All right, here's a few more problems I want to look at. This first one is from chapter 6, number 19, and there's two more that are related to circular motion and Newton's second law. All right, so the first part of this, part A, we've actually already done in the notes. So essentially, there's a plank, all right, and it's lifted up, and they find that this box starts to slip when it reaches 23 degrees, okay? All right, and then after that, okay, after it slips, then they find it slides a certain distance in a certain time at constant acceleration. So I drew that entire picture. So first thing I want to do for part A is they want to find the coefficient of static friction. Well, what I did for part A, as I just said, see the class notes. So that picture would have static friction, so that thing would be F sub S, and that's when contact is broken. So we did that in the notes, and we found that mu sub S is tan theta. So if you take your calculator, put on a book, you lift up your book cover slowly, right when that thing starts to slip, the tangent of that angle gives you the coefficient of static friction between your calculator and the book cover. Okay, that we did in the notes. Part B, okay, now that this thing's sliding, they want to find the coefficient of kinetic friction. So here's our picture. So they asked for mu sub k, and mu sub k is wrapped up into that. So that's why it's a Newton's second law problem. It's a 5-step method problem. Okay, so the problem is if I do F equal ma, trying to find mu sub k, I don't know the acceleration. So they give us this information that it slides that distance in that time. So that means that if I start up here, okay, let's say this is where the box started, broke contact, started at rest, I can use kinematic equation number 2 to find, to express how far this thing went in a certain period of time. So that's 0, initial velocity is 0. They give me how far it went, they give me the time, so I can solve this expression for A. So I can calculate the acceleration based on what they gave me. So I have that. Now it's back to the 5-step method. So I have my picture, I drew my forces. Remember, this thing is sliding. I show it sliding downward, accelerating downward. So kinetic friction points backwards. Okay, there's my kinetic friction force. So I have my picture, forces, coordinate systems based on the direction of A. I broke up my mg. Okay, and then step 5, I do net force equal ma in the x direction. So I have mg sine points down, kinetic friction points backwards, and that's equal to ma. Okay, so remember in this chapter, kinetic friction is always mu sub k times n. Right? Now, you could apply F equal ma in the y direction, all right, real quick, and you would find that normal force points up, that's equal to mg cosine points in that direction. So right here where I have n, I'm putting in mg cosine. So I have this, which I rewrote here, mg sine, minus f sub k, which is mu sub k times n, that's n. Right? Then I got rid of the m's, and then I could solve that for mu sub k. All right, so part A we did in the notes a long time ago, and part B is similar, okay? Picture's the exact same, except that's a kinetic friction force, but instead of giving you the acceleration, they gave you 2 pieces of information, that one and that one, to allow you to find the acceleration. Okay, so here's the problem we didn't get a chance to do in class. Okay, it's not from the homework, but this is a good problem. So you can hit pause and just read through this, all right? So basically you have a clothes dryer, okay? So the clothes are rotating around, that little green thing, like a little sock or something like that, right? And this thing is designed so that it loses contact at 70 degrees, okay? It loses contact at 70 degrees, and it falls back down, okay? It's picked back up, falls back down, so it keeps tumbling. So it's not a centrifuge. It doesn't stay on the edges. It wouldn't get dry and fluffy, right? It's got to fall back down, okay? So it says, they give the radius, and it says when it reaches a certain angle, theta is 70 degrees, that's how it's designed, it loses contact. So when something says loses contact, normal force is 0, okay? So that angle is set to be 70 degrees, and they want to know the number of revolutions per minute the cylinder has to take for that to occur, so that that thing loses contact at 70 degrees. Okay, first of all, I got to figure out what symbol are you trying to find. So we mentioned in class that revolutions per minute is a speed, it's a v, but it's not in units of distance per time, it's in revolutions per time. Okay, and pretty soon in a later chapter we'll see that that's a rotational speed or an angular speed. Okay, so what I did is I drew, so I'm doing, okay, so I want to find V, and V in these chapters is wrapped up into that. So that means it's the Newton's second law problem. So I have my picture, okay, and I'm drawing the forces on the sock. That's my little green sock, okay. So here's where it loses contact. So the only force that acts on it is its weight, mg. Okay, so picture, forces. Coordinate system is based on the direction of acceleration. This thing is accelerating toward the center. That's the direction of the centripetal acceleration, toward the center. Okay, so that dictates my coordinate system. So I chose the radius to be the y-axis, and I chose that direction to be the x-axis. So if mg pointed down, that means I had to break up mg along the tangent and mg along the radius. Okay, so remember, this is 70 degrees. So if that's theta, that's 90 minus theta, that angle's theta. So this is mg cosine, and this one here is opposite, so that one's mg sine. So I'm applying net force centripetal equals ma centripetal. So my picture shows the centripetal force is mg sine. Okay, that's equal to mv squared over r. Cancel out the m's, and I get v. Okay, and r was given. It's designed for theta 70 degrees. Okay, so I just put in the numbers, and I got my speed is 2.1 meters per second. Okay, but that's not what they wanted. They wanted the rotational speed. They wanted it in revolutions per minute. So how we go from distance per time to revolutions per time, we say that one revolution is 2 pi r meters. So I took the speed, and then I said in 2 pi r meters, I have one revolution. And then 60 seconds is a minute. So this is where my meters cancel out. And then this is where my s cancels out. Okay. So that thing would have to spin at about 41.7 revolutions per minute for the sock to lose contact at 70 degrees. At a different angle, right, then that would have to be a different spin rate. Okay, so here's another one related to circular motion. Okay, so I have a curve. It's banked so that this car traveling at 12.75 miles per hour can round it even if the road is icy. So essentially they say that the car can negotiate that banked curve when there's no friction. Okay, and then you want to tell the local police what's the maximum speed the car can go around the curve without skidding, all right, when the road is dry, all right. So the coefficient of static friction is 0.3. What's the maximum speed with which this car can negotiate this banked curve on a dry day? So you were given the information about how fast it can go when there's no friction. Now you want to know how fast can it go when there is friction. Okay, so I just converted that to meters per second. All right, so I drew my force diagram. So here's the car coming at you. There's a center of curvature. So I drew the weight. Okay, I drew the normal force. So picture forces. Okay, coordinate system. Well, remember the car's in circular motion, so that's the direction of the acceleration toward the left. So that dictates my coordinate system. So that's when I broke up the normal force. Okay, so remember it's this component of the normal force, okay, that keeps you moving in a circle. That provides the centripetal force. So picture forces, coordinate system. I broke up n. Okay, that's my angle theta, because that's theta, theta, 90 minus theta. So that one right there, that's my theta. So n cosine, n sine. All right. So first I want to find the angle to negotiate the curve without friction. Okay. So that we did in the notes. Okay. So what we did is we only drew normal force in mg. Okay. There's no friction. So I did net force centripetal equals ma centripetal. So there's my centripetal force, n sine theta, is mv squared over r. Okay. So let's see. I'm trying to find, let's see. Well, I'm trying to find the banking angle. Yeah, I don't know. Yeah, they don't give you the banking angles. You have to find the banking angle. Okay, so find the banking angle so the car can negotiate the turn without friction. Okay, so if I do F equal A in the centripetal direction, I have two unknowns. I don't know the normal force. I don't know the banking angle. So then I apply F equal MA to the car in the Y direction. Okay, so I did that right there. So I have n cosine points up minus mg equals 0. So n cosine points up, mg points down. Okay, so this comes from F equals ma in the Y direction, right? And then I just divide both, right? Or you can solve this one for n and plug it in there, or solve this one for n and plug it in there, okay? Mathematically, it's the same as dividing them. So I divide them, the n's cancel out, the masses m then also cancel out. Okay, and this we did this in class. Okay, so that gives me the banking angle for when this thing's going around at that 12.75 miles per hour when there's no friction. Okay, now the problem says, okay, now there is friction. Okay, I want to find what's the fastest this car can go around the curve without skidding. Okay, so now the car's going fast, it would tend to slip up the incline. The car wants to slip up the incline. Okay, so friction's preventing this, and that's why it points in the direction that it does. Okay, friction points downward. Friction points in a direction that opposes the relative motion between the car and the road. The car wants to slip up. Friction's preventing that from happening. Okay, so I'm trying to find V. Okay, so remember the V is wrapped up into this. So it's a Newton's second law problem. Okay, so I'm doing net force centripetal equals ma centripetal. So I look at my picture. All right, so coordinate system's the same. So everything is the same except, whoops, what happened? Everything is the same except now in this picture, I added static friction. Okay, coordinate system's the same, acceleration's the same. So I'm doing net force centripetal equals ma centripetal. So I look at my picture, okay, I have n sign points to the left, okay, I broke up static friction into its components, okay, that points to the left, that's equal to mv squared over r, okay. So again, I'm trying to find v, and I don't know n, I don't know static friction, okay? So then I applied F equal ma in the y direction. Okay, so I did F equal ma in the y direction. So looking at the picture, I have n cosine points up, static friction sine theta points down, mg also points down, that's equal to 0. Okay, so I just rewrote equation 1 and 2 here. I have my n sine plus friction cosine, and I have n cosine minus friction sine, and I brought the mg over. Okay, now when it's about to slip upward, okay, that's when you're at the maximum speed, that's when static friction is equal to its biggest value. So that's when static friction is equal to mu n. So everywhere where I have a static friction in here, okay, right here where I have my static friction there and there, I can put in static friction is mu n. So I just rewrote these, okay. Static friction is mu n, static friction is mu n. So I put that in right there. Okay. So now I have essentially my two equations, two unknowns. I have n and v. All right. So this is equation 3, that's equation 4. So you could solve equation 3 for n, put it number 4. Or you could solve number 4 for n, put it number 3. Okay. Or you could solve number 3 for n, solve number 4 for n, set them equal. Okay. That's the same mathematically as dividing them. Okay. So I just rewrote equation 3, equation 4, and I divided them. Okay, and then normal forces cancel out, mass cancels out, and I just did the algebra solve for v. All right. Now this step I didn't have to do, but instead of having 4 trig functions, I have a sine, cosine, cosine, sine. Okay, instead of having 4 trig functions, I multiply top and bottom by 1 over cosine. So this term became tangent, that became a 1. This became a 1, and that term became a tangent. Okay, so now I have 2 trig functions instead of 4 trig functions. All right, and I just solved that for v. All right, and I put in the values, okay, and I got my speed, and I converted that to miles per hour. So the car can go around the icy curve with no friction at 12.75 miles per hour. Okay, but a real road or an exit ramp will have friction. So not only do you have a component of the normal force, the n sine that helps you take the bank turn, now you have that component F cosine of static friction that allows you to take it faster. So that's why when there's friction, you can go much faster than the 12.75 miles per hour.